Hi everyone, thank you for joining and welcome to this webinar hosted by Transsolar Climate Engineering and WindowMaster Clearline. Today's presenters will be Krista Palen, Associate Director at Transsolar, and myself, Kasper Ravn, Building Performance Engineer at WindowMaster. During this webinar, you will hear about some exciting case studies from Transsolar, displaying great design approaches utilizing passive ventilation strategies. On top of that, we will also touch some of the various benefits of natural and mixed mode ventilation, as well as talking about some of the modern technologies available to make the operation of natural ventilation more accurate. For the agenda today, we will start by talking about some of the benefits of implementing operable windows and natural ventilation in your building projects. Next, Krista will talk about applications and implementation and design approaches with natural ventilation, including some exciting case studies. And following, I will address some of the modern technologies and talk a little bit about the operation of natural ventilation in general. There are, of course, many benefits of utilizing natural ventilation and mixed mode ventilation in a building project, but I've tried to boil it down to three different main categories. So sustainability, wellness, and resiliency. In relation to the sustainability of natural ventilation, it can, for example, be an essential part of a net zero building or a similar type of building. Utilizing the fresh air directly from the outside will, of course, require little to no fan energy, and will therefore reduce the overall HVAC energy consumption. In relation to net zero or similar buildings, some people will argue that we don't really need to reduce the energy consumption of our buildings because we can just implement a lot more renewable energy like solar panels. However, I think that a lot of building owners and architects will not necessarily be happy with having their building covered in solar panels. And in general, it can also be risky to base your operation of a building too much on the assumption that you will also always have renewable energies available. Therefore, it can be very beneficial, of course, to lower the energy consumptions of your building by using low energy or completely passive systems. So, of course, daylighting is something that is very popular and is a main topic of a lot of buildings. It also has a lot of health benefits related to daylighting. Geothermal heating and cooling systems can often be radiant systems and are very beneficial to use in low high performance energy building. And of course, natural ventilation or passive ventilation can be a very beneficial part of a net zero building, as it uses no to zero fan energy. These systems can also very beneficially be combined. For example, geothermal radiant heating and cooling systems combined with natural ventilation is often a great solution in a building project. A great example of this is House Zero, which is a building located at the Harvard campus in Boston. This is both a research facility, but also an office for the Center for Green Buildings and Cities. House Zero utilizes 100% natural ventilation combined with radiant heating and cooling based on a geothermal system. It also has a 100% daylight autonomy during daylight hours, of course. If you want to hear more about this project, you are, of course, very welcome to contact us after the webinar. Another great benefit of natural ventilation and operable windows is related to wellness. There's many studies that shows the positive impact of natural ventilation on the productivity of the occupants in a building. We have recently written a white paper on this topic, and we can see that from multiple studies that mixed mode buildings with operable windows can increase productivity ranging from 3% to 18%. This is shown to be a result of different factors. One is personal control. Multiple studies have shown a direct connection between the satisfaction of occupants and the amount of perceived control of a building. As designers, I think we sometimes become too set in our ways of how we think the indoor environment should be. And of course, we are the expert, but we also have to remember that thermal comfort and to some extent air quality are very subjective topics. So it might not always be the right solution to dictate what kind of indoor environment the employees of an office building want to sit in. The scientific evidence definitely indicates otherwise. Especially when it comes to higher temperatures, the studies show that occupants can be much more flexible as long as they feel that they have some kind of control. Another point is in terms of wellness and productivity and also health is a reduction of the occurrence of the sick building syndrome. By utilizing fresh air directly from the outdoors, you make sure that the occupants are not, or the fresh air are not polluted by indoor pollutants such as dust and mold. Multiple studies have shown that natural ventilation has a reduction of sick building syndromes such as dry eyes, nose and throat, and a reduction of headaches, and in general, a reduction of low energy amongst the occupants. The last point or the last benefit of natural ventilation that I want to mention is in relation to resiliency. I mentioned earlier that basing your operation of a building on having renewable energies available can be risky. But of course, the main resiliency feature of operable windows is that you can ventilate your buildings and your occupied spaces during emergencies with potential power shortage. The alternative in a sealed building is, of course, to break the windows, but this can have some huge disadvantages in relation to safety, especially in colder outdoor conditions. So with this, I will leave the word to Krista.
Hi, everyone. Thanks so much for joining. Can you hear me, Kasper?
Yes, I can hear you.
Okay, great, super. So I recognize some names from the attendees list. That's great. Thanks for joining. I hope that it is beneficial for you. So now, basically, I'm just going to talk a little bit about just the basics of like the typologies of natural ventilation systems, and then run through a couple of case studies that hopefully you can learn from in terms of your own projects and what things you might need to be thinking about as you're moving forward. So, the ultimate goal is to help more people get to yes in terms of actually getting natural ventilation implemented in their projects. Okay, so just a brief introduction to Transsolar. We are a firm with our head office in Stuttgart, Germany, and we also have offices in Munich, Paris, and New York, which is where I work from. And I'd say okay, I'm just going to keep going. Sorry to start kicked off the call. Hopefully that doesn't happen again. After 25 years of evolution, our approach stays the same, which is that each concept is really individually crafted to suit the project's unique architectural design and the local climate where it is situated. And we call this approach high comfort, low impact. So we want sustainability to be as delightful and comfortable and enjoyable as possible, while having the lowest impact possible on the natural environment. Just quickly going over different typologies. So thinking about natural ventilation systems, I get a lot of questions about which kinds of projects do you need to use manual windows and which types of projects do you need automatic windows. And the truth is that you can use either type of windows with any type of project. They have a bit of different benefits and disadvantages, which I'll go over in a second. But with any type of project, you can use either typology of window controls. And then there's the kind of architectural typologies, which would be something, the most basic would be something like single-sided. So this works really well, for example, in smaller spaces like private office, or even slightly larger spaces, but where you have a lot of window area that you can fit a lot of window area on the wall that actually have operable windows. Then we have cross ventilation. Cross ventilation works best for smaller buildings, but of course there are some typologies if you have, for example, exterior corridors or things like that, where you can get cross ventilation even in a little bit of a more complex building. But the most important thing is that you need to have windows on more than one side. So it doesn't have to be directly across, it can also be a corner. But this cross ventilation works on the principle that you have different amounts of wind pressure on either side of the building. So on the windward side, you have a lot of positive pressure, and on the leeward side, you have negative pressure, and that's what drives natural ventilation through the space. So you get a lot more natural ventilation flow in a cross ventilation scenario than in a single-sided scenario. The next one would be something like single zone stack. So this would be where you have windows significantly higher than your intake windows. Maybe they're in the roof or near the roof on the wall. Basically this kind of typology works through stack effect, just the natural buoyancy of warmer air, and then cooler air creates flow up and out, and then naturally as air comes out, more air comes in to fill up the space, and you get a flow rate. So I'm going to talk about a project where we have this kind of single zone stack, and then these are all kind of the single zone typologies. And then other two major typologies are multi-zone atrium-driven ventilation and a multi-zone solar chimney, or just a chimney ventilation. And these two are actually quite similar, I would say, in terms of the way that they function. The difference would be that in the multi-zone atrium version, you need to really be cognizant about what kinds of temperatures you're transferring into the atrium and the quantity and quality of air that is getting transferred into the atrium, because that's usually the main air that comes into that space. Whereas in a chimney, it's a bit more forgiving, and you're ideally trying to boost the temperature as much as possible with solar energy. And in both of these cases, you will need what is called acoustically protected transfer vents, or if you're in a very unusual case, maybe you do not need to acoustically protect, but you will need transfer vents between the spaces and the atrium, as well as any other joints between spaces that are enclosed. You need to kind of create an air pathway that allows the air to flow all the way to the end. And in, I'd say, any of these three, single zone, multi-zone, or multi-zone atrium or multi-zone chimney, you can do two different things at the exhaust point. You can either have it just fully passive and have it buoyancy driven, which means that it's completely driven by the temperature of the air at the exhaust point, basically, and the outdoor air. So you need maybe like a 5 degree Celsius delta between indoor and outdoor to really make it function. Or you can have a fan-assisted natural ventilation, where you have a fan either in the peak mode, or it's always running in fan mode, either way, and it's running at very low speed. Typically what happens is that you need to have a fan like this anyway for fire protection or smoke exhaust, and it's usually much oversized. You can actually size it. You can actually run it at a very low speed, which is very low energy, especially compared to a conventional air system. And it can sort of guarantee that you're getting your flow that you're originally looking for from your natural ventilation system. Now, I'd say there's probably people who will argue that that's not really natural ventilation. And to that, I would say that that's fair. There is energy associated with doing this. However, the experience for the people in the building of getting to have natural ventilation is very much the same. And I'd say that's a really big benefit of natural ventilation, even more than the energy saved. And this way you can really guarantee particular flow rates that you're aiming for. Okay. So, another thing that was asked for me to talk about was what the high-level design criteria for ensuring a effective natural ventilation design is. And really, it's just the air pass system pressure drop. You have to manage the pressure drop across the whole system, or otherwise it won't work. So all of the opening sizes need to be correct. Your delta temperatures need to be correct in terms of when you're operating your natural ventilation system, and that means that your controls also have to be correct. So all of those things need to be aligned, otherwise there's a very good chance that it won't work. Something we talk about a lot is that, we work on engineered natural ventilation systems. It's not just putting windows that open in a building. You have to actually think the whole thing through. Here's an example of how you can think about the air path through an open window. So, for example, this is an awning window, and the actual open area here is the rectangle that opens at the bottom and the two triangles at the side. Even the top of the triangles, you might want to discount a bit because there's a lot of pressure, or there's a lot of friction potentially that's happening at the top there that might kind of restrict airflow. And then you also need to compare, if you have insect screens on your windows, the insect screens would usually be on this flat square part. And what you're always looking for is the smaller of the two, because the smaller size is the one that is the limiting size of your airflow pathway. So you'd kind of compare the sum of these triangles and this rectangle to this square divided by half. Say if you had a insect screen which was reducing, had a 50% openness factor, then you would take the smaller of the two, and that would be the size that this window was giving you for open area for your air to flow through, for example. And now on to just quickly a little bit of thoughts about manual versus automatic windows. I think that they're both great. I think that there's certain cases where automatic windows are pretty much needed, and that would be where windows are inaccessible. So let's say you have an atrium and you have windows up high in the atrium, or any kind of tall spaces where you're having windows up high, then you absolutely need to have automated windows, because if people cannot easily access windows, they won't operate them, and if they don't operate them, the system doesn't work. But that being said, a lot of times people kind of come and they say, well, we can't afford automatic windows, it's not affordable for us, so we can't do natural ventilation. And I would say that's definitely not true. If you have a simple design of a building, you can absolutely have not manual windows and it can still work fine. The more complex the design, I think the more beneficial automated windows are. But even if you still have a complex design, you don't necessarily need it, as long as you have some alternative indicator system that tells people what they should be doing in a really clear way. Basically, I'd say actually even things like individual offices are much better with manual windows, because when people kind of have ownership over a particular space, they tend to kind of get frustrated when there's something that's kind of over operating for them, versus in something like a classroom or a larger space like an atrium, then people don't have that expectation that that window is theirs to control, and they won't control it anyway, so it works really well when it is automated. And I think, in some of our projects where we have manual windows, but they have a really great indicator system of natural ventilation mode, and they have a lot of buy-in and they've done a lot of education, that people are really empowered to open the windows. Like that moment when the building goes into natural ventilation and everybody opens the windows is like kind of community building. Like I think it can be a really great thing for the right building. That being said, automated windows give you some extra benefits. One of the really big ones is a controllable night flush mode. So you can crack the windows late into the night without too much concern of safety or things being left open for rain or things like that. All that can be very controllable. And a night flush mode can really reduce your cooling demand, especially, or your peak sizing of your cooling system. So I think it can be really beneficial for the right building that has enough thermal mass to benefit from it, and in the right climate that has a pretty big diurnal swing. It is more expensive. It's also, another thing that's great is that you can regulate the open sizes of all the different windows so that the overall flow rates are controllable by some kind of central system. That could be really beneficial. Another great thing about automated windows is that they typically are an opt-out system versus a manual window has to be an opt-in system because we require people to take a step to open them. An automated window, you can have them open, and then if people don't want it open, they can override. They can have an override button that says no, close it. But you don't have to wait for people to join in order to get the whole thing working. Yeah, lots of communication is also necessary to make sure that occupants understand how to override, how to control them, so that they don't feel that the building is alive and is working against them, for example, and that the windows don't need to be physically accessible. Okay, so the first case study that I'm going to talk about is the Carl Miller Center that we worked on with Danish architect quite a few years ago now. It's been under operation for maybe a year and a half. And what I would quantify this building as is atrium-driven, fan-assisted natural ventilation with automated windows. That's what's in this building. So this was an existing building on Portland campus. It's the Portland State Business School. Kind of a cool building, but definitely out of date. And you can see like this whole metal component came in 79, and then this was phase 2. And then just keep building on. And then this is what we completed in 2017. The existing building, we tore off the exterior and put a new facade on. And we attached this atrium here in the center and what we call the pavilion here, which is a bunch of additional classrooms added to the school on this side. And basically, the whole concept for this building was based around the idea that we would attempt to do no mechanical cooling in the pavilion whatsoever. So the air supply system doesn't have cooling, and there's no additional radiant panels or any other system right now in this building, in this part of the building, to do cooling. It is in Portland. They have a great climate, and we want to take advantage of that as much as possible. Another thing is that this atrium actually is very tucked away. This is the north side of the building here. So the atrium is basically fully protected by the existing building in terms of solar. We didn't have to do a lot of shading on it or anything. It was fully protected. And we actually only have windows located on these classrooms on the north facade as well. So there's really not a lot of solar gain, which really helped us get ahead in terms of minimizing the heat that we would have to disperse. That being said, these are classrooms. They have high occupancy, a lot of people. So we still needed to get a fair amount of air changes in order to have enough cooling effect through the natural ventilation system. You can see that the strategy was very heavy on thermal mass, which is absolutely critical in this case. So thermally massive floors, thermally massive ceilings, and some acoustic panels to cover up, but keeping everything in balance as much as possible. What you're seeing here above the classrooms, these are some of the acoustically protected vents that go between the classrooms and the corridor. And those are critical components. They're always the hardest to design because they are, in order to be acoustically protective, they have to have a lot of acoustic baffles in them, and the acoustic baffles fill up the space, which means the free area is very limited. So, these are the piece in every system, I think, where it takes the biggest mental hurdle to accept how much space that these may take up. And the more the better, because the less pressure drop you have from things like this, the more free-flowing the whole system is. So this is kind of basically how it works. As I mentioned, there's only windows on the north side. This one on the edge actually doesn't go into the atrium on the top floor. It just uses cross ventilation. And that's, again, not uncommon for our buildings, but some spaces have a different strategy than the other spaces, just based on their architectural configuration. And that should be fine, especially a space which is quite high up has a lot more wind pressure than a space that's low. So then that's more driving force to get the natural ventilation through. The rest of the spaces here, for example, air comes in through automated windows, which open up once the building goes into a natural ventilation mode. This red is the transfer vent, and then it comes into this atrium space. We were careful to design the exhaust point as the most negative point of the atrium, so we kind of peaked above the existing building, and the wind generally comes from this direction, and this is a negative point. What you don't ever want is you don't ever want your exhaust point for your passive natural ventilation system, or even if you have a fan-assisted natural ventilation system, to be going directly into like a windward side of the building. If at all possible, you always want to be creating a little negative pressure zone so that air releases as freely as possible and doesn't get pushed back inside the building. Yeah, that's basically how this works. We do have a kind of comprehensive comfort strategy for this building. They were willing to accept up to 83 degrees Fahrenheit, 28 degrees C. My understanding hasn't gone above 80. We do have ceiling fans. We have thermal mass. We have and we worked a lot with them, and we took them to different test facilities and things like that so they could feel what it would be like with ceiling fans. And everything, all of the comfort that was used for this project is still accepted comfort in ASHRAE 55. Just some more shots of what the project looks like. This is the atrium. So the classrooms are separate from the atrium, but then there's no more walls between the atrium and the corridors. It's quite open here. But the atrium as well, has quite a lot of thermal mass. And it's working really well, this project. Right, this is just kind of how we got to our design in terms of the configuration, minimizing solar gain and optimizing the thermal mass, as well as utilizing ceiling fans at different speeds and how many hours you would have actually in different comfort ranges. So in the end, we actually did have 32 hours that were, by simulation, above the uncomfortable threshold, and they were willing to accept that. So that was a decision that they made. I think in reality, our assumptions were quite conservative, and we haven't had anything like that, actually, that I know of. Right, and this is just right now the EUI. The original building's EUI was 53 kBTU per square foot. The new building's EUI right now is 24 kBTU per square foot, and it was about $330 per square foot to build. The next project I'm going to talk about is actually still in design. We're kind of entering construction documents. So it's possible that some things may change in this project, but as of now, this is kind of what is designed. This is a project that's in Toronto. It is being designed by Moriyama and Teshima Architects, as well as Acton Austri, out of Vancouver. And it's a mass timber building. It's, I think, 12 stories tall. And and it's a school for design students, both architects and graphic designers. This is a large atrium that we have coming in. You can really see there's a lot of mass timber. Everything's mass timber, all of the structure, floors and ceilings. There's actually not very much thermal mass in this building. This is part of the natural ventilation system that I'll come back to, but these are what we call breathing rooms, which are basically the entrances to the solar chimneys. And this is how this building works. We have passive mode. So what you're seeing here are classrooms. We have manual windows in this building that people will open when they have an indicator system that tells them that it's time to open the windows. The air will, and the ventilation air and the radiant panels will shut off automatically in natural ventilation mode. And the air will transfer through acoustically protected transfer vents, which are a slightly different design than the other ones that I showed before, sort of like just over the wall kind of system, like a small crack at the top of the wall where the wall meets the ceiling. And then it goes down the corridor in either direction. There's solar chimneys located on either side of the building, where the air kind of goes up and out through those breathing room spaces. So I'll just go flip back to the breathing room for a sec. So yeah, these are the actuated windows that open into these chimneys. And the chimneys have these solar shading in the interior of the chimney to try to build up as much heat as possible in the chimney and not allow that solar gain to kind of come into these spaces and bake them. And then in active mode, basically we have semi-decentralized air units. We have 2 per floor that fit into these rooms here, and the air is brought in from this side, for example, and then we have underfloor air distribution, VAV diffusers that deliver the amount of air which is necessary based on CO2 control. Air kind of follows the same pathway as in the natural ventilation system through the acoustically protected transfer vents back to the corridors, and then gets brought into these small rooms for energy recovery, and then out back to the outdoors. So one really nice thing and a really good strategy to use in your hybrid natural ventilation buildings is to use the same air pathway that you are using when you in your active system and your passive system, so you don't have to have a bunch of extra stuff that you're not, so that it ends up costing the project more. The more you can reuse the same pathways, the more it can save money. So another thing to just think about is your chimney operation modes. So in natural ventilation here, the bottom of the chimney is closed. The louvers into the chimney from each floor are open, and the top is open. This is a system where we actually have manual windows, and we do not have any fan assisted mode. This system has to work completely passively. So that means that because we'll have different stack effect on every floor, each floor needs to be designed a little bit differently, and everything needs to be in balance in order to make sure that you don't get overflow from one floor and then resulting no flow on another floor. But I'll talk about that a little bit more in a second. In heating mode, what happens is you just really seal this up as much as possible. The roof is, the exhaust is sealed, the bottom is sealed, and the space is sealed. So this ends up acting like a double facade in the winter, and it actually gets very warm. And because it has a lot of solar access, it gets very warm and will help to heat these spaces in the winter, and they really don't require any other heat actually beyond being adjacent to this wall, at least during the daytime. And in cooling mode, what you don't want is that same thing to happen as in heating mode. So what happens here is we open up the bottom and the top. The louvers into the building are sealed, and this just flushes as much as possible. So anytime heat builds up, it's naturally going to want to just escape, and that will bring cool air through the bottom. So it shouldn't get too hot in this space, and that shouldn't create extra cooling in these spaces. This is just a little bit of a closer look at what's happening in the space level, but I think we've kind of gone over that already. Underfloor air system, and this is the transfer vent here. This is an individual classroom. So I think we haven't decided exactly what the indicator system is in this building, but this is just some examples of things people are doing. You know, there's a huge range of things that people are doing for natural ventilation indicator systems. I think that this is an area where there's a huge need for good designers, interaction designers, wayfinding people to come in and design systems that are really clear in terms of telling people what to do, what's going on in the building, because too often you see things like this one in the bottom corner where it's just a light with a switch or something and nothing is labeled. And if people don't understand what's happening in the building, they're going to have a really hard time using it properly, and that's just a shame. So I think things that can be as instructive as possible are great. Whether we really need things like iPads in every room, I think that might be overkill. You know, it's great, but maybe it's not necessary. I think there's some in-between strategies that can work really well. This is just a little bit about the energy use intensity for this building. This project is in Toronto, where they have and they've started these new absolute energy standards, which are really fantastic. And this one's kind of hitting the highest tier for energy. They also have started including thermal energy intensity targets. So that's, you know, the heating that's required before you apply any kind of COP or any plant efficiency. Really a measure of how good your facade is. And so that's, you know, another thing that's been included, and this building is performing very well in all those things. You know, this project is a bit complex in terms of how the natural ventilation system is designed. So here you can see this is an example of how we would do an airflow pathway on the path. So for every floor, we have indicated, you know, what kind of windows we have on the exterior transfer vents. These are all sized, and then, you know, into the corridor, into the breathing rooms, into these solar chimneys, and all of this stuff is sized. And here's an example of, you know, taking the worst airflow pathway on every floor and looking at how that compares to the stack effect that will be available at the design point of your system. You can see, like, windows, for example, are very low pressure drop of the whole system, but the transfer vents are quite a lot. And then even things like dampers in the chimney can actually be a lot too, because at that point you have all of the air coming together, and the more air that you're trying to push through a particular orifice, the bigger the pressure drop will be. And then this building, you know, we actually have a lot of interconnections from the atrium and the lower floors, as well as different stairways, which are really great for the system being really active. But you have to be conscious of that air will flow through the path of least resistance wherever. So we have kind of a network airflow model to make sure that, you know, the air isn't short-circuiting any particular zone, and that all the zones will achieve their target airflows, both for ventilation and for cooling. So you always want to make your target airflows for both of those two things, and the ventilation are always lower, but they're the most critical one. And then for cooling as well, so that, you know, you get the most benefit from your system. In this project, because we have quite a modular design in terms of each floor has its own air handling unit, and each space has VAV diffusers that are controlled by individual CO2 sensors. If any one space decides they don't want to be in natural ventilation, it doesn't impact their other spaces. They just shut down, they can close their windows, and they will run with the mechanical ventilation, and the other spaces will continue to run in natural ventilation, and it doesn't have any impact. So it's really flexible that way, and I think it's going to work really well. Okay, so the last case study that I'm going to talk about is this project that we worked on with Karen Timberlake a couple years ago. for their own space. Some of these slides are taken from a presentation that I did with them at Greenbelt this year. But this is what their space looks like. It's beautiful, big open space. And this project I'll classify as a single zone stack effect with automated windows and fan assisted exhaust as well. So it's this, they basically purchased this old bottling factory and turned it into their office. This is what it used to look like, and then this is what it looks like now. Very open, collaborative workspace. This is basically the concept that they had. So when they first took over the space, they were very ambitious and did not install any mechanical cooling in the space, and they wanted to only have natural ventilation in the summertime. So it was fantastic, and they spent a lot of time and effort doing things like comfort surveys to understand how people were comfortable or uncomfortable, and they spent a lot of time tinkering with the system to kind of try to see if they could get it to work. Fortunately, it was not a success, although they tried for a long time. They eventually found that they did need to install mechanical cooling, and then they kind of came to us and asked us to help them to create a hybrid control system that could allow them to still absolutely minimize the amount of time that they spend in cooling and maximize the time they spend in natural ventilation. So as we were coming into this project, they were just in the process of installing automatic windows for this row here, the automated windows. They already had these exhaust fans on this roof monitor here. So that was already part of the system. They do have floor diffusers that are not VAV, but they're manually adjustable. They do have fans and they use floor fans and desk fans as part of their strategy. And they have a policy of people being able to wear whatever they like during the hot season to make sure that they can stay comfortable. They also have a very decked out sensor system across their whole space. So they really included a ton of sensors across the whole space, in the walls, in the roofs, in the floors. Like it's actually crazy. It's so much that you wouldn't think that it would be useful, but we ended up finding it to be very useful for this project because as part of this project, as we were after we agreed to take on this project, they had a second request, which was, would it be possible for us to do a calibrated energy model based on different seasons where they had done natural ventilation to make sure that the controls that we're recommending were going to result in comfort. So this one I'm just going to skip over quickly. This is ROSE, that's their comfort program, where they were kind of identifying where people are comfortable and not comfortable. Again, they're finding that temperature was having a big impact and not humidity on their comfort, and that they felt like basically, after all of their efforts of trying to get their system to work without cooling, it just wasn't possible because above 84 degrees, people were really unhappy, and they had about 35 hours that were above 84 degrees. This is a very old building, not insulated, and it does get hot in the summer in Philadelphia. So that's just what it was. So that's why they decided to install the cooling. But there was still tons of time in the yellow there that they could use really benefit from natural ventilation, or especially using like a night flush mode. So this was the kind of control system they presented us with, that their controls guys had taken what they had asked for and turned it into this spaghetti of logic, and asked us to bring some clarity to it. So we did this energy model calibrated to their measured data and some historical weather files for the location. We were able to get lots of real specificity with the design, because they had all the drawings, they have all the construction. We have a shading mask of the nearby buildings. We have all of the different stuff that's happening in the different zones. So they have underfloor air. This is a Transsolar model that has 4 different air nodes, and we have different kinds of mixing equations for the air between all the nodes. We have occupancy schedules because they had quite good data of exactly how many people were there at different times. And we had all these sensors. So the sensors that we ended up calibrating to were 4 of these different middle of the zone air node sensors. So there was one in the occupied zone, sort of a mid-pole, a truss level, and a clear story level mode. So basically to represent these 4 air nodes, as well as a node in the underfloor plenum, but less relevant in air conditioning, in natural ventilation mode. So we took a week of each of the different seasons. So we started with heating, and we modeled each of the different zones. And we had really good match in heating because it's kind of the most mixed. It's the most mixed time, and also I think there's the least impact from solar that kind of messes up the other data, which I'll show in a second. We're struggling to figure out a way to see how well is this calibrated to reality. So we just made up this metric, which unfortunately has been a little messed up by the PowerPoint, but basically it's the percent of hours that the modeled version is less than degree Fahrenheit difference between the 2 models, basically. And this is what in the occupied zone, which is of course the most important. So we had almost 80% of the hours less than 1 degree Fahrenheit difference between the modeled and the measured in the occupied zone. And then this is in the overall for all 4 zones, air nodes. And again, this is the summer chiller mode. Once they started having cooling, matching that as well. You can see that actually the clear story is the one that's not matching very well here. And we figured out that that was actually because the measured data is getting direct solar. It's getting hit by actual sun. So that's throwing off. The real measured data is actually the incorrect one. And the model data is probably closer to reality in terms of what the air temperature is in that zone. But if the sun is hitting either the sensor itself or the things around the sensor, and then radiating to the sensor or heating up the air around the sensor in a more intense way than the other air, that can kind of mess up your data. So that was really interesting to always remember that sometimes measured data isn't the most accurate thing, and if you have to think about the thermodynamics that are happening around your sensors. And then finally, we did a passive mode calibration. And again, there's a little bit of that impact on the solar hitting the clear story zone, but it's not too bad. Overall, we were really happy with how well we were able to calibrate the model to the measured data. And then just touching on control sequences, this is kind of the breakdown that we have of the space. So there was a lot of concern about things like pollen. So we have a mode that if there's ever an air quality concern, that we go into an economizer mode. And then above 12 grams per kilogram outside of absolute humidity, we go into cooling mode, or above an outdoor air temperature of 78. And then we also invented a new mode, which we call heating light, which works in this building, especially because these buildings, they don't have energy recovery. So basically, this allows them to really just barely crack the windows and use the perimeter floor heating around the exterior to top up the air that's coming through the windows, not to make it hot, but just to make it so that the people sitting adjacent to the windows are not being too cold, and there's still actually a lot of cooling power in that air for the rest of the space, and it works fully passively. Otherwise, like it's because of delta between indoor and outdoor temperatures is so high during that point. It works really well with like very small openings and still allow people to have this experience of fresh air into like the more winter side of the shoulder seasons. So we proposed a bunch of different modes. I won't go too far into each of them because I think we're kind of running out of time, but we proposed a bunch of different modes from a really conservative mode to our most extended natural ventilation season mode. And then we mapped those to different time in each of these operation modes. So this is the amount of time that you're spending in each operation mode for the year. So the way to read this is that you have 24 hours on the y-axis and every day of the year on the x-axis. You can see from the baseline we spend a lot of time in cooling, and then in the most extended natural ventilation control you spend only 10% of the year in cooling. So big difference between about 38 and 10%. And then on the flip side, the same kind of mapping, but this is actually of temperatures that are being experienced inside the space during this time. And what's interesting about this is that actually these don't look that different. You know, although the modes that you're spending time in are quite different and the energy associated with being in these modes is quite different, the comfort that can be achieved with proper controls, they found that it was, it's actually quite, or we found it's quite similar between all of these different cases. And, you know, in the end, they decided to go with the full natural ventilation controls just because they felt like people had suffered enough in the past, so they might consider pushing it again in the future. But for now, this is what they went with, so that the space never goes above 80 degrees, basically. And they only have to spend about 15% of the time in cooling. 32% of the hours are still in natural ventilation. It's just another way of looking at the same data. We really got into the details of how to do the controls for this project, which I think was really helpful and interesting in terms of exactly how each component works, and it's something I'd recommend that you think through for all of your natural ventilation projects, is like exactly what is happening. If you're controlling your natural ventilation system by a CO2 sensor, you know, how is that working? Which part's opening? When is the exhaust fan turning on? All that stuff is super important and is sometimes not something that traditional mechanical engineer is going to take the time to think through. So it's really important that somebody does it. And this is just looking at the reduction in fan energy, which was the big savings here is the reduction in fan energy and some cooling energy as well, from not having to use the mechanical ventilation system for the entire year. And this is sort of them on track to be below the other years in terms of their energy consumption compared to when they installed the cooling mode and from before they installed the cooling modes. And then just a little bit about cost. I think this is coming from them, but very often it seems that, you know, the project has natural ventilation in it, has automated windows, operable windows, or even this kind of indicator system, and the price comes back from the cost consultant really, really high, blowing the budget or something like that, and then it kind of gets kicked out of the project. And I think this is just kind of sharing that, you know, those prices are often are incorrect, or just the result of people being a little bit inexperienced with this kind of thing. And it's really useful to contact a manufacturer or something like that and get your own kind of sense of what the cost of things are. So that you're just being realistic about it. So here's an example of unit cost for their own project. They ended up having a unit cost per window for all of the automation and everything of $2,000 per window, including all the controls. And then for contact sensors for the windows, for just a manual system where you just want to know if windows are open or closed or not, it was about $440. Yeah, so lots of lessons from this project. One thing I forgot to mention, a big overriding learning from this project of doing so much in depth on the natural ventilation controls was that the mode of the controls should only be based on the outdoor conditions, not the indoor conditions. So whether you're in heating, natural ventilation, cooling, or some other version of a mode, that really is only dependent on outdoor conditions. What happens inside that mode should be dependent on the indoor conditions. So that way you don't end up kind of getting a lot of recursive functionality in your operations that make it unstable. And if you find that you cannot maintain comfort within one of the modes, then what's happening is likely that your set points between the modes based on your outdoor conditions is incorrect. And I think that's probably it for now. Another slide.
And now we will talk a little bit about modern technologies available in the market to optimize the operation of natural ventilation and operable windows. Krista has, through her presentation of her case studies, explained how natural ventilation can be controlled based on temperature and air quality. Here I just wanted to provide a quick overview of the potential operation of an automatic natural ventilation system, where we of course control based on measurements of the temperatures, the humidity levels, the CO2 concentration, and the wind condition. Based on these factors, we can calculate not only the required airflow rate to ventilate a given space, but we can also calculate the actual airflow rate being supplied through the operable windows. Another level of control would be to measure the actual wind pressure on the different facades of the building. However, this is not really a feasible solution to mount wind pressure sensors on the facade of a normal building. An alternative for this that we use in many projects is that we do external CFD simulations before the commissioning of the projects. This allows us to take the surroundings of the building into account and find wind pressure coefficients on the specific parts of the building facade. We can look at specific areas of the building and calculate how much the attached operable windows need to open to achieve a certain ventilation rate. As an example, we can look at this corner room of the building and figure out how much the windows should open specifically in this room based on the surroundings, floor levels, and orientation. Based on these external CFD calculations, we can also find the most optimal location of the weather station. However, the location of the weather station becomes less critical as we also know the relationship between the measured wind speed of the weather station and the actual wind pressure on the facades. But all these calculations, simulations, and measured values will of course be redundant if we don't have the technology available to actually operate the operable windows accordingly. For a high quality natural ventilation system, we will have a good integration between actuators, motor controllers, and the building management system. The building management system will of course process the measured data and dictate the operation of the actuators. However, modern actuators will also have the ability to report back to the motor controllers and to the BMS. It's therefore a two-way communication system. This will allow us to have very accurate position control and will also allow us to have perfect synchronization between multiple actuators. With modern technology, we also have the ability to operate the actuators at different speed levels. This is crucial in relation to the noise level the actuators produce. If they operate at a very high speed in automated mode, we risk creating issues for the occupants. Therefore, it's very important that the actuators can operate at low speed when they are automatically controlled by the BMS. However, at the same time, you potentially want some noise feedback when the occupants are manually controlling the windows. Not a lot of noise, but just a subtle indicator. This is especially true if the windows are out of sight. We also see in modern systems that operable windows can be controlled by an app on a cell phone. And this also means that the occupants need some kind of feedback that the windows are actually operating. We also want to make sure that the windows still have the ability to close quickly when it starts to rain, for example, or during certain emergencies. As mentioned before, the two-way communication between the actuators and the BMS also allows for perfect synchronization between the actuators. Why is this important? If you have multiple actuators on one window, you want to make sure that they operate at the same level at all times. Otherwise, we risk the windows being damaged. Multiple actuators are, for example, used on parallel pop-out windows. As an example, you can see on the picture to the left. This type of window will usually require 2 to 4 actuators per window. In other examples where multiple actuators are required, could, for example, be an awning window if it exceeds a width of approximately 4.6 feet. We have two great examples of the parallel pop-out windows being used in projects. The first one is the Bullitt Center located in Seattle. This is a very ambitious building which utilizes natural ventilation very well to achieve great HVAC energy savings. Another example is the PNC Tower in Pittsburgh. Here the operable pop-out windows are attached to a double-skin facade, which both transfers fresh air to the office spaces and the occupants, but also allow the occupants to use the double-skin facade as an artificial outdoor space where the employee can take a break. It's estimated that natural ventilation can be utilized approximately 45% of the year. An interesting fact about this project is that the productivity and wellness of the building was a greater selling point for natural ventilation in this project than the cost savings of energy savings were. If you want to know more about these great projects, you are very welcome to contact us. To finish the webinar, I want to talk about some of the experiences we have learned from making natural ventilation systems through the last 30 years. This is also something that Krista touched in her presentation. And it's a lot about the thermal comfort of people and the perception of thermal comfort. So 2 points that we have found from experience when it comes to thermal comfort in building is that we see a positive behavior where people are allowing higher temperatures in the summer times if they have or they feel they have control over the indoor environment that they are located in. As Krista also mentioned, it can be enhanced by the use of, for example, ceiling fans, whereby creating air movement inside the spaces, occupants can accept higher temperatures. Another point is that we have found that during the winter, it can be okay to introduce cold air into the occupied space as long as the zones are otherwise comfortable and we only introduce the cold air for a short period of time. For this, we use something we call pulse ventilation, where we only open the windows for a short time, maybe 2 minutes. And during these 2 minutes, the occupants will not feel the discomfort of cold air. They will feel it's more refreshing. So these points are something that we have found are maybe not something which can be measured by simulation software. The predictions are not always equal to the reality. It's something that often is found after commissioning of the projects, that the occupants actually have another preference than what was indicated by the simulation software. This was all we had for you for today. Thank you so very much for joining the webinar, and thank you for listening. If you want to know more about Transsolar's great projects and natural ventilation system and the use of natural ventilation in general, you're of course very welcome to contact us after this webinar. Also, a great thanks to Krista Palen and Transsolar for letting us learn about their great projects and giving us insight of how they design with natural ventilation. Thank you so much for joining.